Grade 12 Physics, Energy and Momentum, Note number 5, Introduction to Momentum and Impulse. So finally we're going to get to the second half of our unit, where we're going to examine the momentum of an object, and in today's note, the impulse of an object. If we think of inertia, inertia is a property of motion, then momentum is a quantity of motion. So if we look at motion, we can actually give it a value where momentum is represented by the willingness of an object to keep doing what it's doing. Here we use the variable p for momentum. It is a vector quantity. The momentum will be in units of Newton seconds or kilogram meters per second. Mass needs to be in kilograms. Velocity needs to be in meters per second. If we look at the units, left side Newton seconds, right side kilogram meters per second, which are both acceptable for momentum. Let's do a quick example here. Let's compare the momentum of a transport truck and a pickup truck. So let's say they're traveling down a highway, both going at 36.5 meters per second. That's pretty close to about 100 kilometers an hour. Let's calculate the momentum for each of them. So we're going to make two calculations here. We need to know the mass, which will be written here. First we're going to do the transport truck. Transport truck, let's say, is about 4,000 kilograms. So here P equals mv. So it would be 4,000 times 36.5. We get a final momentum of 14.6 times 10 to the 4 Newton seconds. Let's compare it to the pickup truck here with a mass of 1,500 kilograms. Putting that into our equation, P equals mv. We're going to get a final value here of 5.5 times 10 to the 4. So almost a third of the momentum of that transport truck. So here, even though they're going the same speed, because that transport truck's heavier, it's going to have more momentum. So what we're going to now look at is impulse. The best way to compare impulse with momentum is comparing acceleration to velocity. We know that acceleration is a change of velocity. So that means if we compare it to momentum, impulse is a change of momentum. If we're going fast to speeding down and then stopping, we have a change of momentum in that time, so we have an impulse. To derive a formula for impulse, we're going to start with Newton's second law, F equals ma, where we know acceleration is a change in velocity over time. So we can sub that in. Let's expand the top and move that time factor over to the force. We know that P equals mv, so we're going to get P2 subtract P1, which that basically is just change in momentum now on the right side. So Ft equals delta P, and that's what our goal was to find, the change in momentum. Instead of writing delta P all the time, though, we use the variable J. So here J equals Ft. Impulse equals force multiplied by the time. So what does this equation mean? J is impulse, and because it's a change in momentum, it has the same units as momentum, Newton seconds or kilogram meters per second. Force is in newtons, T is in seconds. So let's use this as an example here to see exactly what we're dealing with. Let's say a hockey player is going for a body check and he misses his body check and he slams into the boards. Here the impulse is going to be about 1,000 Newton seconds, which is reasonable for a 100 kilogram hockey player moving at 10 meters per second. And the time taken to stop him, so he's going at that full speed and then he comes to a stop in 0.2 seconds. Let's calculate the force supplied by the boards to stop that hockey player. So we rearrange the formula and we do our calculation. We eventually find it's 5,000 newtons. It's going to take quite a bit of force to stop that hockey player in such a short amount of time. So impulse values end up being quite large. In many cases, the value for J is constant. If we examine the same collision over and over again, our change in momentum will be the same. So in that case, if J is constant, if F or T change, the other variable is going to also change to compensate. So here, if we increase T, Knowing that we have the same value of J, that means F has to decrease. But if we decrease time, if we shorten the time of the collision, force must increase. So overall, the two equations we're dealing with, J equals Ft, and J, which is the change of momentum, mv2 subtract mv1.